Hello, class. Welcome back to our series on strange partition identities. So again, today we're going to use generating functions to prove a pretty bizarre partition identity. So I'm going to define for you two types of partitions. I have named them type A and type B. Please note that they're not known by the names type A and type B. I just wanted to have two names to talk about, so I just called them type A and type B. Okay, so let's start with our type A partitions. So our type A partitions are partitions where all of the parts are 1 or 5 mod 6. So I've gone ahead just to make sure we're clear on what 1 or 5 mod 6 means. It means either 1 or 5 more than a multiple of 6. So I've gone and given you a pretty large example here where n is 20. And so how did I do this? Well, I originally said, okay, if I want parts that are 1 or 5 mod 6, what parts could those possibly be if the sum is going to be 20? Well, 1 or 5, and then 1 and 5 more than a multiple of 6, which is 7 and 11, and then 1 or 5 more than 2 times 6, which is 13 and 17, and then 19. And then the next number that's 1 or 5 more than a multiple of 6 would be 23, but I can't possibly have a part that's equal to 23 in a partition of 20, so I'm just not going to worry about it. Okay, and so then I wrote all of these down. Note, many of these partitions have lots and lots and lots of parts equal to 1. So I just sort of started just smearing the marker as we wrote down all the parts that are 1, because all of these are written in decreasing order. But you can algorithmically do this, again, just by saying, okay, well, I'm going to start with the largest part, which is 19. Well, the only thing that could go with it is 1. Okay, and that must be the only partition that starts with the 19. And then the next largest one, I now basically forget that the 19 exists. And I now look at the 17 and say, okay, what's the next largest thing I could take? Well, the only thing I could put here are some 1s, and then that fills that out. And then so on and so forth. So this is basically the algorithm we've been using this whole time. Okay. So these are sort of specialized only in the sense that I've thrown out any partitions which are not, or any valid or any numbers that aren't 1 or 5 mod 6. Okay, but otherwise, this works just like partitions. And so anyway, if you believe my list here and you check and verify that I did not leave anything out, then you will agree with me that there are 20 such there are 18 such partitions of 20. Okay. Next to that, we have partitions into distinct parts, which means I never repeat anything, but not just distinct parts, but distinct parts that are all not equal to all not a multiple of 3. Okay, so if I write down partitions, all of which are into distinct parts that are not a multiple of 3, then I can write these down here. And so I, again, just to produce this, went ahead and wrote down all of the possible things that could be involved in a partition of 20 that are not multiples of 3. And you go ahead and start again with the highest term. Although you have to be slightly careful because you can start with a term and find out that there aren't any ways to go from there. So for example, how do you know you're done? Well, when you get to starting with the largest part being 7, the largest you could possibly get would be 7 plus 5 plus 4 plus 2 plus 1, which as it happens is 19, so it doesn't quite make it to 20. Okay, and so I've given you here, I think, a pretty non-trivial example of what the claim is going to be that we're going to prove today, which is that there are always the same number of type A partitions as of type B partitions. Again, sort of what you might try and do is you might try and say, okay, well, maybe there's some sort of combinatorial proof that will give me that by establishing a way to translate between the things on this page on the left and the things on this page on the right. Good luck. I'd be very interested if you found one. But it is not so easy to figure out how one would go about that. Okay. But it's not so bad to do this by thinking about the generating functions. So I'm going to do this. I'm going to prove this for you by writing down the generating functions of these things and proving to you that the generating functions of type A partitions and of type B partitions are actually the same. Okay, so I'm going to leave these 2 pages over here so you can remember what type A partitions are and what type B partitions are, and I'll work here. Okay. Of course, this is an equality, so I could start with either side, but I think it's a little more natural if I start with the type A partitions. So I'll start by writing down the generating function of A of x. So the generating function A of x, that's the sum as n goes from 0 to infinity of A of n times x to the n. And so what is that? Well, that's going to be partitions into parts that are 1, or 5, or 7, or 11, or 13, and so on, as we did there. So this is going to be 1 plus x squared plus blah, blah, blah. That's my partitions into 1s, or my parts equal to 1. 1 plus x to the 5th plus x to the 10th plus dot, dot, dot. That's my parts that are 5. 1 plus x to the 11th plus dot, 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 and so on. Okay, and so ultimately, as we probably are pretty happy with by now, this is going to get turned into 1 over 1 minus x times 1 minus x to the 5th times 1 minus x to the 11th. That's a 5, by the way. It looks kind of like a 3. 1 minus x to the 13th, and so on down the line. Okay. So what are we going to do here? Well, I notice that B of x, or sorry, B, or type B partitions involve things that are not multiples of 3. And it might occur to you that 1, 5, 7, 11, 13, 17, 19, and so on, those are all not multiples of 3. But there's some numbers that are not multiples of 3 that are missing. Namely, we're missing the numbers that are 2 and 4 mod 6. And so in an attempt to make this product look more like something that's going to be involved in type B, I can try putting those things back in. So similar to before, I'm going to add a bunch of terms here. And of course, I can't just add terms willy-nilly. So the terms I add, I'm going to put in both the numerator and the denominator. Okay, so I have 1 over 1 minus x. But then I'm going to add here a 1 minus x squared and a 1 minus x to the 4th. But I need, in order to add those, to also put those in the numerator. Again, this is just a really complicated way of multiplying by 1, so I have not done anything too complicated. And then I will continue. Next, I add 1 over 1 minus x to the 5th. Times, and I'll do one more line before I put the dot, dot, dot. So I've got 1 over 1 minus, oh, I skipped 7 here. Sorry, when I wrote this before, this was supposed to be, I just randomly skipped 7. So this is that term that I missed when I wrote it there. Oh, I also skipped it here. Sorry. Okay, so there, now we've got this. But I need to put in, between the 7 and 11, I'm going to put in the 8 and 10, which are also not multiples of 3. So 1 minus x to the 8th is 1 minus x to the 10th. And as I've gotten ahead of myself, I need to also put these things in the numerator so that I'm not changing the thing. Times 1 over 1 minus x to the 11th. And I keep doing that. Okay. Now what am I going to do? I'm going to slide all the terms in the numerator over so that instead of having all of these ones, I'm just going to skip all the ones because the ones in the numerator aren't doing anything. So I'm going to write this like this. Okay, and so then times... Okay, and I'm trying to keep track of where the terms came from by the color. So the red ones are the ones that I sort of invented. So that's there. Okay, so now the denominator here is a 1 minus x squared, and the numerator is a 1 minus x to the 4th. Okay, and of course you might notice, hey, I'm sort of tempted to cancel this 1 minus x squared with this 1 minus x squared. But if I do that, then I'm undoing all of the work that I have done so far. By sort of introducing these things. So I instead, ultimately, just as a prediction of what's going to happen, I'm going to need to cancel this 1 minus x squared with this 1 minus x, and this 1 minus x to the 4th with this 1 minus x squared, and so on down the line. Okay, so what's the next denominator? The next denominator, and I'm just following along here in order, is 1 minus x to the 4th. And what's the numerator that's going to go with that? It's the next none-1 numerator, which is 1 minus x to the 8th, times... Okay, and so now my next denominator is 1 minus x to the 5th. And my next numerator is 1 minus x to the 10th. Okay, and I'll put... and so on here. And now... much like before, what's happening here is that I am having a bunch of differences of squares divided by one of the terms of the differences of squares. So 1 minus x squared is 1 minus x times 1 plus x. So when I cancel the 1 minus x with that, I'm left with a 1 plus x. Okay, likewise here, 1 minus x to the 4th, that's 1 minus x squared times 1 plus x squared. So cancel the 1 minus x squared, and you'll get 1 plus x squared. Okay, and so on down the line. This is 1 plus x to the 4th. This is 1 plus x to the 5th, and so on. And so what do I have here? Well, after I sort of collapsed all of this, I have one term for each power of x that's not a multiple of 3. And they all look like 1 plus... and then that power. So I have an x to the 1st, an x to the 2nd. I don't have an x cubed because that's a multiple of 3. And then I have an x to the 4th and an x to the 5th. And I don't have an x to the 6th because that's a multiple of 3, and so on and so forth. And so then you have to ask yourself, well, what is this the generating function for? What problem is this answering? Well, that's not so difficult because I'm sort of saying, okay, how many ways are there to combine this? And for every term, I either choose that power of x or not. And so, in fact, actually, this is exactly describing to me the type B partitions, because it's describing to me the partitions that have distinct parts, because the thing just stops here, and it's distinct parts that are not divisible by 3. And so, in fact, this thing we've just written down, that's exactly what you would write down if you'd started with the B side. So that is B of x, which is... I'll remind you that's the sum as n goes from 0 to infinity of b of n times x to the n. And thus, we have proven, because these two, again, power series are equal, that means their coefficients are equal. And so, thus, a of n is equal to b of n. Okay, and so I did not just randomly choose the number 20 and have it happen to work out that way. It works that way for every n. All right, we're going to wrap up for the week there. Next week, as a preview, we're going to be starting to talk about graph theory, which has lots of applications, including notably recently modeling virus spread, unfortunately. But it has lots of other applications that we'll talk about. So that's something we'll sort of split that topic into 2 weeks worth of subtopics because graph theory is a pretty enormous area. But until then, have a wonderful day or week or weekend or whatever time, night, whatever time it is you happen to be watching this. Definitely let me know if you have any questions about anything I said in the videos or anything, homework or anything. You can post it on the forum. You can come to the office hours I've started advertising on YouTube. You can send me an email, whatever. Any way you know how to get a hold of me. Just let me know if there's anything I can do to help. Until next time, be well.